Solutions to page 1 of the Contextual Applications of the Derivative Study Guide. With problem number 1 and with the next few problems, we're dealing with L'Hopital's rule. With problem 1, we want to find the limit as x is approaching pi. So we need to plug pi into both the numerator and the denominator. Obviously, we can clearly see that the denominator is going to go to 0. When we plug pi into the numerator, we have the cosine of pi plus twice, or the sine of 2 pi rather, plus 1. The cosine of pi from our common value chart is negative 1. The sine of 2 pi is 0, so negative 1 plus 0 plus 1 also produces a 0. So 0 in both the numerator and the denominator, so L'Hopital's is in effect. So we're going to continue with the limit as x approaches pi, but now we need to derive the numerator and the denominator separately. Well, the denominator's derivative is rather easy. X squared just derives to 2x. Pi squared is a number, right around 10, so it derives to 0. Up in the numerator, cosine derives to the opposite of the sine of x. For the sine of 2x, we need to use the chain rule. The outer function is sine, the inner function is 2x. So sine derives to cosine, keep the inner function, and then that gets multiplied by the derivative of the inner function, which is 2. The 1 will derive to 0. Now we're going to plug pi in again. So we now have the opposite of the sine of pi plus twice the cosine of 2 pi, all over 2 pi. The sine of pi is 0. The cosine of 2 pi is 1, so we have 2 times 1. 2 times 1 is obviously 2, and we're going to divide that by 2 pi. So we see an answer of B. With problem number 2, we plug 1 into the numerator, 0. We plug 1 into the denominator, also 0. L'Hopital's. So we continue to take the limit as x approaches 1. Derivative of the numerator, nice and easy. Derivative of the denominator is one that we're used to. Natural log of x derives to 1 over x. So when we plug in 1, we get a very clear 1 as our answer. With problem number 3, we're going to plug 0 in for x. So we have e to the 0, which is 1. 1 minus 1 gives us a 0. Obviously, we have 0 in the denominator. Once again, L'Hopital's is in effect. So we now have the limit as x approaches 0. When we derive the numerator, e derives to itself, and 1 derives to 0. When we derive the denominator, x derives to 1. We're interested when x is 0. So we have e to the 0 over 1. Anything to the 0 power is 1. So the answer, once again, is 1. This time, though, it'll be C. Now we're going to switch over to related rates. Let's get this all on the screen here. When we do so, we want to start by identifying the information that we know. All right. We are told that the radius is changing at a rate. Here's our word change, only it's disguised as increasing, and we can verify this with the units. Right? We see we have 3/10 inches per second, so our units are a fraction. Right? Linear over time. Well, r is not a fraction, right? But dr dt is, and r is in linear units and time is in time units, so this matches perfectly. So dr dt is 3 inches per second. We're told that the surface area is 100 pi. Save that for later. All right, square inches. And we're trying to find the rate of change of the volume. So dv dt is what we are looking for. So if we're looking for dv dt, it's probably a good idea to start with our volume formula and to derive it. Now we're going to derive this with respect to time. We can derive with respect to time as long as we do it to both sides of the equation. So we derive the left side with respect to time. V, well, that's just a single variable. So just as x derives to 1, v derives to 1. But we have to multiply it by the derivative of v with respect to t. So the left side of our equation will now be dv dt. Over on the right side, 4/3 and pi are both coefficients, so we know from our constant multiple rule that they will move right into our derivative. R cubed will derive to 3r squared, but again, because we're deriving radius with respect to time, we need dr dt in our derivative. Now we can see that our 3's are going to eliminate each other, so dv dt is actually 4 pi r squared dr dt. But 4 pi r squared has already been mentioned in the problem. It's our surface area. And our surface area is 100 pi square inches. So this 4 pi r squared is going to get replaced by 100 pi. And dr dt is going to be replaced by 3/10. We put the two of them together and we have 30 pi. So our answer is E.